This is a video about continuous functions. So let's let a be a subset of the real line. Let's let f be a function from a to r, and let's let c be a real number. And for right now, let's say that c is a cluster point of a. So like there should be stuff in a that's arbitrarily close to c. All right, so I want to remind you of something first. So recall that a real number L is the limit of this function as x approaches c. And what does that mean? So here's this epsilon delta definition. For every epsilon that's positive, there should exist a positive number delta, such that if here x is within delta of c, and I'm specifying for limits, right? I didn't want x to actually be equal to c. Limit is about being close to c, not actually at c. Then though, f of x should be within epsilon of L. What I want to emphasize about the limit definition up here is this does not say that L has to be an output of your function. I'm not saying f of c has to be L. So to give you a picture of maybe what's one thing that's going on, so if I show you this picture down here, there's my function is in that kind of reddish color there. And the point then is that if I was to put this any blue window around L here, I could find a corresponding kind of pinkish window around C so that for any x value that I picked in that window, the corresponding y value is within that blue window to the left here. And so what I want you to notice then though is what's the actual value of this function at C? Well, the value of the function at C is definitely not inside that blue window. So this is an example where the limit of as x goes to c of f of x, it's equal to L, that's fine and dandy, but that's not equal to f of c. So that's what I want you to see here. So what we're going to focus on is, well, what are the functions where it is equal to the output of the function at this cluster point? That's what we'll call continuity. That's what we'll call continuous functions. So I'm going to erase some of this stuff. Bear with me while I do that. All right, so if c is actually an element of a, so in other words, all I'm trying to say there is now it makes sense to plug c into my function. Maybe it didn't before. We could still talk about limits when your function wasn't defined at a particular point. But now if it does make sense to plug c into our function, we'll say that f's continuous at c if the following happens. So I made these two things the same color, and what I hope that you notice is it looks exactly like the limit definition to the left. So this limit definition, or this epsilon delta definition of continuity on the right over here, it looks almost exactly the same as this limit definition over on this side, but maybe what's different, here I'm saying it's fine if x is equal to c, and what else am I saying? I'm saying that L can't just be anything. L has to be the output of the function at c. So this says that yes, the limit as x approaches c of f of x has to be f of c. So that is a key feature of what it means to be continuous. And so this is the epsilon delta way to say you could draw its graph without picking up its pencil. And so to give you an example of that, or maybe a picture of such a graph, I can't have any weird holes with like a big jump going on between them, something like that. And so in particular, it makes sense to plug c into my function, and I see again for any blue window that I put around f of c, I could find a corresponding small enough little pink window around c here so that for any x that you picked out of that pink window, when you plug it into your function, the corresponding y value always lands between f of c plus epsilon and f of c minus epsilon. Cool. All right, so there is a sequential criteria for continuity, which probably isn't too hard to believe. How come? Well, because there is a sequential criterion for limits that we talked about, and continuity is kind of based off this idea of a limit, where what if the limit is actually the output of the function? And so what is the sequential criterion for continuity? Again, your function is continuous at a point c in your domain if and only if for every sequence xn that converges to c, the sequence of outputs f of xn ought to converge to the output f of c. And to give you an example about why this might be useful, this is useful for trying to show something is not continuous. Instead of not continuous, I'll probably say discontinuous. And so as far as the proof of this goes though, if you look back at the video that I made about sequential criterion for limits, just replace all the L's you saw there with f of c, and it's the same proof. So where might the sequential criterion for continuity be useful? It's probably useful to show something is not continuous at a particular point. So let's think about this function. F of x is this piecewise thing that it's 0 if x is non-zero and it's 1 if x is 0. And I claim that this function is just discontinuous at 0. I'll draw you a picture there and you see that, well, he had to pick up his Apple Pencil at 0 in order to draw the graph, right? There's this big jump here. So what I want to do is show you the sequential criterion up here. So if I want to show that it's discontinuous, I'm going to negate this. So that means I should be able to find some sequence that converges to C, but the outputs do not converge to f of C. So that would be the negation of that again. Okay, so let's think about what's a good sequence of inputs that converge to the point 0 here. And well, my favorite sequence that converges to 0, besides just the constant sequence of zeros, is the next one. My next favorite is 1 over n. So the limit of xn, in this case, is 0. But what happens when I plug in any non-zero number into this function? The output's 0. And so, well, in particular, all these xn's, it's always 1 over n. That's never actually equal to 0. Therefore, when you plug in 1 over n into your function, it should give you 0 back. So the sequence of outputs of this sequence, that's a lot to say. The sequence of outputs of xn is just the constant sequence 0. But what's the limit of a constant sequence? It's just the constant. That limit should be 0. So the limit of f of xn should be 0. But wait a minute, what's the value of my function? Well, that's 1, and 1 is not equal to 0. So what did we just show? I just found you a sequence of inputs whose sequence of outputs, right, does not converge to the actual output of the function. So that might be one way that you might try to use the sequential criterion for continuity. What else have I got for you? So going back to the epsilon delta definition, how would you show that something like f of x equals x squared is continuous at 0? And I just picked 0 because it's nice to work with. So just to remind you, so given epsilon that's positive, you want to find a delta that's positive such that if x is within delta of 0, then x squared should be within epsilon of the output, or 0 squared. I try to emphasize that's me plugging 0 into that. So it should be within epsilon of 0 as well. And so to remind you how these go, you always start here and kind of work your way backwards to come up with this delta. And when you do that, right, that's where we emphasize again that delta is typically some function of epsilon. So if I start there, that says x squared is less than epsilon. Go ahead and try to solve that for x. That says x should be less than the square root of epsilon. So this would be a pretty good delta to pick, right? If delta was the square root of epsilon up here, then I've got x is less than that. So therefore, when you square both sides, you'd have x squared is less than epsilon. So how would I do that a little bit more formally? In other words, what's the argument? So in green, this is the scratch work. How do we pull it all together? So your proof would look like let epsilon be greater than 0 and choose delta equal to the square root of epsilon. Then what happens? Well, if x minus 0 is less than delta, or if x is within delta of 0 is a more accurate way to say that, then, well, I don't really need to write this 0 here, so think about squaring both sides. Well, then x squared should be less than delta squared, but delta is the square root of epsilon, so that's just equal to epsilon. And you proved it. Now, what did this do for us right here? It was a little bit subtle. That justified that the limit as x goes to 0 of x squared is equal to 0. Just remember for continuity, we just need to make sure that that 0, right, this L, is actually the output of my function at c, which again, c is also 0 here. So because that is the case, I can say that f is continuous at 0. I've got one more weird function for you. So what do a lot of mathematicians do? What did they do? Still do, continue to do, but when real analysis was kind of getting started, mathematicians tried to make all sorts of weird functions to see how far these definitions would stretch and what could we do with them. So here's one pretty famous weird function. It's called the Dirichlet function, and it's defined as follows. F of x is 1 if x is rational, and it's 0 if x is irrational. So this is how I'm going to say, like, that's the set complement, or set minus r minus q. Those would be my irrational numbers. I claim, though, that this f is not continuous at any x and r. So it's discontinuous everywhere is another thing you might say here. So how do you prove something like this? What's one idea? We'll recall that the rational numbers are dense in R. And what did dense mean? I'll give you one idea about what dense meant. That means that given any real number, for any epsilon, there should exist a rational number that is within epsilon of x. And so to give you a picture of that, if I was on a number line and I plop down any x that I like, and I put any blue window around x that I like, I'm guaranteed to find some irrational number inside that blue window. I don't care how tiny epsilon is, there's guaranteed to be some irrational number, in fact infinitely many, inside of that window. So here's what we're going to do. If that's supposed to work for any x and r, and for every single epsilon, right, no matter how small this window actually is, what I'm going to do is I'm going to let epsilon be 1 over n, where n's a natural number, and I'm going to let Rn be that rational number that should fit inside of that window. So such that x is within 1 over n of Rn. And so in that case, if I could do that for each natural number, right, what do I got? I've got a sequence of Rn's, and they're getting closer and closer to x, right? As n gets large, 1 over n gets small. So in general, I've just built you a sequence of rational numbers that converge to x. I could do that for any real number that I like. So what I'm going to do is I'm going to do that for, as in particular, an irrational number. So for any irrational number you give me, who I'll also just name x for right now, what do I know? Well, by the above, I could make you a sequence of rational numbers that converge to that x. And so in particular, what should I be able to do there? Why is that important for me? Well, if you were to plug Rn into your function f up here, Rn's rational, so that should give me 1. So f of Rn is equal to 1 for all the natural numbers n. So in that case, the limit of f of Rn, that's just the constant sequence, 1, 1, 1, 1, 1, so the limit is also 1. But what should it be? What is it not, actually? So 1 is not equal to 0. I feel pretty good about saying that. But that's f of x, right? If x is irrational, then f of x should be 0. So what did we just do? Again, we use the sequential criterion to help us out here. I found a sequence such that the limit of the outputs is not actually equal to the value of the function. It's not actually equal to the output of the function at x. So what that just showed is that f is discontinuous at all the irrational numbers. So we're halfway done, right? Because, well, the other half is the rational numbers. But note that the irrationals, those are also dense in R. So you could do a very similar argument where you could construct a sequence of irrational numbers that get as close to any rational number that you like, and therefore do a similar kind of idea with the sequential criterion up here. So that would finish that f's discontinuous at all the rational numbers as well. So what did you do, or what do we have now in total, right? Well, f's discontinuous at all the irrationals, and also we just kind of talked through how you might show that f is discontinuous at all the rationals. Well, therefore, it's discontinuous for every single real number.